This talk is going to be different than, I think, past and future ones. On one hand, it'll be digging into lower level details. On the other hand, I will sketch, kind of skim over them. The main takeaway message being not the details of what we've done, but rather essentially a bag of 3 tricks that were done in the context mostly of NAND flash, but we believe that are applicable to various extents to other technologies ranging from DRAM to future memristic, etc. The 3 things will be constrained coding, speculative early sensing, and minimum maximal level programming, and I'll explain as we go along. So just for those who are already fully in Memristive and forgot what flash is about, some key things that we will build upon here. In flash memory, the reading entails basically first pre-charging a capacitor, then providing a reference voltage, waiting for a while, and checking whether that capacitor has discharged or not. You do it several times, thereby determining the level, the threshold voltage of the cell. Programming, because in flash you cannot remove charge incrementally or selectively, you have to provide kind of shots of charge and then see whether you've provided enough, if not, another cycle, etc. The reason will become clear, I mean, the relevance will become clearer very soon. Also, kind of underlying assumptions or realities, a larger level increase takes more time than a minor one, and more precise programming takes longer because you need to nail it exactly, you need to give smaller shots. And many cells are programmed concurrently. This is something to remember as well. Now let's move into the first issue, which is constrained coding. I'm intentionally holding back on what for. When you look at the flash memory cell, when you come to read it, ideally for each level, the threshold voltage should be a specific value level, 0, 1, 2, and 3. In practice, you have distributions. Think of probability distributions. The reasons are various. One is that the programming is done with limited accuracy, so depending on where it landed. And a major factor that's becoming more and more pronounced is interference from neighboring cells. That the charge level there affects through stray capacitances the threshold voltage of the cell that we're talking about. The intercell coupling, this is just a schematic that shows you that there are these inter-floating gate capacitances that we would like to have, but they are nonetheless there. And the result is that instead of having narrow distributions like you see here, they are widened. In fact, if you look carefully, they're widened in one direction because you can only pull in one direction. There are no charges the other way. Insights from all this. The program and verify, we said charge is added in small increments, and we repeatedly test until we reach the desired threshold level and stop there. What this means is that the threshold voltage of any given cell, when we finished programming it, was perfect to within the accuracy of the programming. Because what we see takes into account the effect of the neighboring cells at that time. However, if we later add charge to the neighboring cells, this changes the threshold voltage. So the threshold voltage of any given cell is affected only by charge that is added to its neighbors after its own charging has been completed. And therefore, this depends on the programming order, programming scheme as well. There are schemes for mitigating this effect. One is proportional programming, which says, basically, let's, in the first shot, provide every cell, let's say, nominally 70% of the charge. Different amounts, because their target levels may be different. Then in the next shot, another, until they reach it. Ideally, they're all programmed simultaneously, so everything will be okay. However, programming is very slow, very complicated, so it doesn't really work. An alternative approach is, let's program without taking this into consideration. Indeed, the threshold voltages will be affected. But when we read, we will decode using a technique called successive interference cancellation used in communication, meaning we know that the last cell to be programmed is unaffected. So we read it. Then we say, okay, the effect of it on the cell that was programmed next to last is such and such. So we can cancel it and know what that one should have been given what we read. However, this requires that we read threshold voltages, detect them in a much finer resolution than just the levels, because we need to account for partial level shifts. So can be done, but not simple. Our approach comes from a totally different world, from the coding world. We say, and coding people may view this as some kind of an abuse of coding, but we don't care. We basically forbid the use of adjacent cell level combinations that cause too much intercell interference. The criterion depends on the programming order, and the threshold is a design trade-off. The more we restrict the interference, the more combinations are prohibited, so we lose capacity, but the narrower the distributions. So when we program, we use only permissible combinations. These are the legal code words. So given the data, we convert to legal code words and code. And in reading, we use the inverse mapping and detect it. So the pros are, we limit the effects of intercell coupling. It's as if we chop the tails of the distributions. What we lose in capacity is the area under those tails, incidentally. Fairly simple encoding and decoding. And unlike other schemes, we don't need to know the exact intercell coupling parameters of a specific chip, or even instance of a chip. We just need to know upper bounds when we see if our threshold may be exceeded. The cons are some loss of code rate or capacity, but not necessarily of capacity, because if we can add levels, it may more than offset the loss. So basically, when given a chip and a program order, we derive the interference or disturbance function to a cell, impose the limit, and forbid the threshold, and forbid those combinations that exceed it, then construct an encoder, a decoder, and go to work. The main contributions of the work we did on this are characterization, formulation of the coupling, etc., in relation to the programming order. We proposed the schemes to do it. We have some examples of encoders, etc., that work. But now to the question that I skipped at the beginning, okay, but good for what? You know, in English, there's a nice expression that doesn't exist in Hebrew, good for nothing. It's good, but what for? So narrower VT distributions, the first use could be to say, okay, so we have more room now, we can add levels. This is true, but unfortunately, the storage capacity increases only as log base 2 of the number of levels. So it won't buy us much. Another approach may be to leave it as is, enjoy the larger safety gaps between the distributions, and this may permit us to go to the next technology node while maintaining the same number of levels. This is fine, but that's in the future. You know, always easy to sell things for the future. Question is, can we do something now? And the answer is actually yes. We can program faster. Because remember, the total width of the distribution accounted for several things, one of which was the sloppiness in programming. If we reduce the effect of a major other contributor, we have more room for sloppiness in the programming. If we can program in a more less precise way, it means we can do so faster, fewer rounds of programming. So we can go in bigger steps. So we can actually, started with intercell interference, applied coding to narrow the distributions, and the benefit, the most likely benefit, is actually reducing program time. Let's move to the next trick in the bag, which is speculative early sensing. And here our purpose is to reduce read time. Now in reading, as I said, we pre-charge a capacitor, then apply a reference voltage to check whether the threshold voltage is above or below, wait for a while, and then the sense amplifiers check whether this capacitor is discharged. How long do we wait? The manufacturer specifies a wait time based on worst case, over chips, temperature, age, God knows what, takes some spare, and goes with that. In all likelihood, one can do usually substantially better. So our approach is speculative early sensing. We simply wait less. The problems, this of course may result in read errors, but we do not destroy the data. It's just a read error. And if we have a read error, we need to retry with a longer time. But there's still a challenge of how do we know that there's a read error? Because just signatures, any bits can flip and you don't know what's what. And okay. So here, the general scheme is very simple, that we set an initial time, read. If we detect errors, we retry with a longer time. If everything's okay, we stay with that. We may in the background reduce the time. We can learn, quote unquote, study the chip over time, regions in the chip, etc. These are secondary optimizations. But the question is, what about errors? And here, an important, critical observations. The errors are unidirectional. Because if we see that the capacitor has discharged, it is discharged. If we wait another hour, it'll still be discharged. The only possible error is that we see it appears to have not discharged, but actually we didn't give it enough time to discharge. So if we speak of charged as a 1 and as a 0 and discharged as a 1, then the only possible error is that a 1, which should have been a 1 discharged, appears to us as a 0. And this is the key to the solution. We use what's called Burger codes. In addition, alongside with the data, let's say n bits of data, we store a signature which is simply a binary number, log n bits, saying how many zeros there are in the data. Now, if you think of it, in the data itself, if there are read errors due to us, the number of zeros increases. When we read, is larger than what it should be. The signature as a binary number, the number can only decrease if a 1 looks like a 0. So the only case in which the numbers will match, the signature that we read will match the number of zeros in the data as we read it, is if neither was disturbed. Now, so this can detect any number of errors caused by us with certainty, provided that there are no errors in the other direction due to other reasons. The technique can similarly be used for DRAM, and the issue of offsetting errors is highly unlikely for the following two reasons. One is we can still use conventional signatures. It will detect that with high probability. But also, when we set the time, we will not set it to be something marginal. So the likelihood of an error because of us with tuning is very, very, very low. And if errors begin, they will probably be major errors, much more than a random bit flip, so we will detect it anyhow. Okay, the final topic I want to talk about is back to more serious coding of sorts. And we call it minimum maximal level programming. It is aimed primarily at shortening program time. And this hinges mainly on the observation that if you need to change levels by a greater amount, it will take you more time. Also, we program thousands of cells concurrently. So in a set of thousands of cells, there will always be a cell wanting to go from level 0 to maximum level. So the programming will always be slow, or worst case. There have been suggestions to do things differently. For example, multi-page programming says, in the example of 4 levels, including the erase, and so 2 bits per cell, each page owns 1 bit in the value of the level. So the first page only uses level 0 and 1, and therefore is programmed fast. And the second page may bring us to any level, that will be slower. Our approach is different. We do the following. I'll illustrate it in an example of 4 levels, again, 4 including the erase. So think of 4 pages that we want to write. 2 bits per cell, so we need, if we have n bits per page, we need 2 n cells. So we have 2 n cells, 2 bits per cell, so 4 n bits, which is okay, 4 pages. The first 2 pages, the first page, we use n cells and level 0 and 1, conventional, fast writing. Second page, we use the other n cells, level 0 and 1, so far so good, fast writing. The third page, we use all 2 n cells, so we basically place half a bit per cell from this page, and we know how to do it in a manner, to encode in a manner that we only need to use level 0, 1, and 2. We do not touch level 4. So programming here may entail going from 0 to 2, but not 0 to 3, so it is not as fast as 0 to 1, but kind of, let's call it medium. And only the fourth page, which again is smeared across 2n cells with half a bit per cell, will use all 4 levels. So basically, in terms of write speed, we will have 2 fast, 1 medium, and only 1 slow, where the slow is what would have been for every page originally. Here you see an example. I won't go into the details, but the first 2 pages don't need any encoding. It's obvious, 1s and 0s. For the third page, for any pair of cells, given the current state of those 2 cells and the bit of the third page, we decide what values to put in those 2 cells. The only thing to point out is that you will see that there's never a drop in the level, because we cannot reduce levels. So going from left to right, the new level will always be greater than or equal, higher than or equal the original one. And similarly, for the fourth page, we now depend on the levels, again, of the 2 cells, and same idea. So looking on the left at write time numbers, this factors in all kinds of statistical things, but let's say for a given set of numbers that a conventional thing would take 800 microseconds, with multi-page 700 roughly, we bring it down to less than 500. Looking at read time, if the page is fully, if the cells are fully written, we wrote all 4 pages, then we need to know which of 4 levels any given cell is at, and we need the full read time. If, however, the cells are not fully populated, so let's say we start with virgin cells, as long as only 1/2 of them is occupied, namely only pages 1 and 2 at the bottom, we have fast reads. We only need to determine level 1 or 0. Then, once the third page, we need to know whether it's 0, 1, or 2 for any cell. So it's longer, and only for once everything is there, then for all pages, it'll take the long time. Beyond 4 levels, there is a scheme for actually increasing this to any number of levels. The idea is simple. We take, this is the 4-level structure, we duplicate it, so we double the number of cells, and also we double the number of levels. these are programmed as we described, and then the remaining 4 pages, we're going up to 12 here, are smeared across 4n bits, and then we can take this whole thing, double it, again add levels, etc. The final point I want to touch very briefly is what happens about when the number of levels is 2 to the something, then obviously capacity matches, everything matches. But what if we have, let's say, 6 levels? Are we okay at these intermediate levels? And the answer is yes, roughly hand waving. It's because when we add for every additional page we put, we need linearly more capacity. The capacity versus levels grows logarithmically. Because the derivative of a log goes like this, if we're okay here and okay here, we're definitely above the linear in between. So this is hand waving, but it's actually correct. The open issue is, there is an open issue. We showed that the capacity is okay. The question is there a path that doesn't entail reducing level at any stage? We haven't proved it formally so far, but by construction, up to 16 levels were okay, provably by construction. So in summary, I think I summarized that. The things you heard, we basically added to the more or less controller level, constrained coding, speculative early sensing, MMLP, and something else I didn't talk about, retired page management. This is a teaser if people want to hear about it then later. So in conclusion, the main topics were constrained coding, which gives us faster writes, or other things if we want, early sensing with error detection, faster reads, and indirectly faster writes as well, because the cycle, the verify cycle, becomes faster. And MMLP, faster MLC, where M is multiple, any number of level writes. The important kind of takeaway messages beyond the specifics, cross-layer approaches can be effective. Coding is a very versatile tool, not just for coding purposes. And applicability to future technologies depends on similarity of the underlying properties that I mentioned at the beginning. Thank you.